looking at samples and how they vary, hence the title, Variability of Samples, but specifically linking to distributions that we're familiar with. So we're going to start with a uniform distribution, and we're going to look at generating a series of samples. We'll start with a discrete uniform because we've done discrete and we've done continuous. And then we're going to move on to different. So your calculator actually generates random values based on distributions as well. So not just when you do random number generator, it is and collector random. It is based on uniform distribution. So all the sampling we've done so far on the calculator is based on a uniform distribution, but it also does set up for different distributions as well if we want. But we're going to start with discrete uniform, and we're going to look at generating a series of samples. So let's go with the first one. We've got a game that requires rolling a 10-sided die, and so we're interested in the number that is rolled, and I think I probably gave this away, what type of random variable this is. Be careful though, because in last year's WACE, if you did not write the actual type of uniform distribution, I think last year's WACE it was continuous, you did not get the mark. It asks for what type. So it's discrete uniform. Just writing uniform is not good enough. So discrete uniform, and then you could say, I don't know, different ways of doing this. 1 to 10, where x is an element of the set of integers. Or you would have to say where x equals and list them all out. You can't just use that range and not specify that we're talking integers, because otherwise it looks like it is continuous. Exactly. All right, what's the PDF going to look like? Have a go writing it down. And I guess in this case, we certainly, as the PDF, need to write those integers. Or, like I said, you've got that range as long as you say it is an integer. All right, what's the histogram going to look like? So 50 observations, so that's 50. Then we've got potentially 5. We would expect, in theory, and I guess we could just make this really quick. This really needs to be done with a ruler, and all those columns should all be evenly spaced. No need for gaps. In fact, no gaps, and that's what it would look like. I guess we should put f of x and x just to be pedantic, but potentially, you know, you could lose marks for not doing the right labels, etc. If you do it in stat mode, you can see the list of numbers. So we just need to go and call up the random number part to the calculator, just rolling across to R and rand list. Oops, didn't mean to do that twice. And we want 50 between 1 and 10. So by default, your calculator generates the random numbers as a uniform distribution. And there they are. So by doing it in stat mode, at least you can see the count, the fact that you've got 50 numbers, and then you can either tally or just count up how many ones all the way through 10s you have. Just be careful the graph, because look at the way that 1 potentially should be straddled, should be centred here. Then the 2, 3, but that's all my data. And so it does say draw a relative frequency graph, so there it is. There's my graph. And you can do the same. So on your calculator, you've got to go to this icon here, set stat graph number 1, that make sure the draw is on. Then you go to type, so I've said histogram, because I think by default it's scatter plot. First move is to, hang on, let me just get out of there. Is just to press that little graph icon. No, it won't let me get out of there. Come on. That thing, that one there. Yep, that one, and then you make sure the drawer is on. So you can potentially draw a whole heap of different graphs, right? But we'll stick with number 1. And you do need to change the type to histogram because by default it is scatter. X list 1 frequency is 1. That's it. And set. But just and then H start H step. So start at 1. I just want to try something. If we start at 0.5, what happens? Just out of interest. Okay, that's better. Yeah. So if you start at 0.5, you will then potentially get the numbers as they should be centered. The way I did it by starting at 1 means that it wasn't centered. So start at 0.5, go up in 1, and that's better than what I had before.
Oh my gosh, it's actually really fun.
All right, then from there it just makes it easier.
That's a bit different.
That can go now.
I like a lot of 7s.
It just makes it easier now to see the frequencies as opposed to you having to count them back, up to you. And of course, this is the frequency. I've asked you to draw the relative frequency. So we've just got to convert those frequencies to essentially probabilities, which is your relative frequency. So this next example is continuous uniform. Yeah. So your 2 endpoints. The middle of the 2 endpoints is the expected value or the theoretical mean. The standard deviation, if you remember, we did have a formula. I think it was A take B squared on 12 or B take A squared. Doesn't matter, either or, because you are squaring anyway. So the square root of that for the standard deviation, 5.774 to 3 decimal places. So theoretical mean, theoretical standard deviation. Now, as I mentioned, your calculator, when you do RAND, only generates a uniform continuous distribution, but it's between 0 and 1. So to get it between 30 and 50, I have given you some instructions on the next page. It's pretty self-explanatory, and hopefully it makes sense. So you've got 30 is your start point, right? The first number's got to be 30 or somewhere between 30. And then because the difference between 30 and 50 is 20, that's where the times 20 comes in. So times 20 RAND, and it's RAND, using RAND list actually, and putting in 15. And then that'll give you your uniform, the decimal numbers between 0 and 1. And then you could, so this is just a different approach. You could do this in stat like I showed you, or you could do it in main. It's a different approach where you actually tell the calculator, put it in list 1 in stat mode. So it allows you to see it in main and put it in the list as well. I don't know, whatever. It's just showing you a slightly different method. So that symbol, that implied symbol, is found on the calculator through the keyboard. You get, so you'll all have different means and different standard deviations. Each sample will be different. And really that's the point. Now, if I look at mine, analysis, sorry, not the graph, analysis, get out of the graph, sorry, go back to my list, and go calc, 1 variable stats, list 4 is the one that's got 500. There's my mean, and there's my standard deviation, 5.739.6. Now, what we decided was the theoretical mean was 40 and 5.7. That's pretty close with 500 numbers. Now, for those of you that did 15, did you get close enough or not? Yep.
A whole lot closer when you do 250 though.
Yeah, whole lot. So I'll go, so list 2, let's say, was my one that's only 15. And then I'll go calc. I'm wanting to work out my, oh, there it is, 5.6. That can't be right. Done something wrong. Anyway, the point is, yeah, the more observations you have, the closer to the theoretical mean. You can see from the graph that I drew before. But also, each sample you do is different. And if you look at the persons next to you, they'll have a slightly different mean, a slightly different standard deviation. And this is leading us into the fact that we are trying to decide whether our sample is appropriate or not. It could be a bias set. So in a real life situation, if it's not matching what we suspect in theory, it could be a bias sample. And so if it's too far away from the mean or something's not quite right, then potentially the sample could be biased. It might not be. It could be just what we're looking for. And so this is where it links, or we'll be looking at some work to do with confidence intervals, where we have an interval in which we are satisfied that the mean, or for specialist people it's mean, but for us it's proportions, might be. And at the moment we're just looking at samples, so just playing around with that for the next lesson or so.